Okay, so welcome to third session of Joerg, Analytic Geometric Langlands-correspondence relation to Conformal Field Theory and integral models. Please.
Yeah, okay, thanks very much. Yeah, I shall continue where I left yesterday. So what I did yesterday was to interpret at least some aspects or some parts of this geometric Langlands correspondence from the point of view or from the perspective of integrable models, and the D modules in particular can be made more, the D modules appearing sort of on the right-hand side of this correspondence as initially presented, can be represented quite concretely as eigenvalue equations. And sort of the new idea, which is underlying what is now following Ittinghoff, Frenkel, and Kashtan called analytic Langlands correspondence, is to combine both the holomorphic eigenvalue equations that somehow the geometric Langlands correspondence is initially about with their anti-holomorphic partners or counterparts. So to study the combined system of these equations, and then to look for natural and reasonable supplementary conditions which define a well-defined mathematical problem and which can be interpreted, say, from integrable models perspective as quantization conditions defining a spectral problem. And good, so it has these kind of two layers or two versions. One can, and this is what I did in the work from 2017, one can impose as such a condition just the single valuedness, which in any case is a reasonable thing to do. But of course, ultimately, if one has in mind, say, spectral problems as arise in quantum mechanics, or say the analogy to the theory of automorphic forms, so to bring the Langlands correspondence back closer to the theory of automorphic forms, then conditions like square integrability would appear natural. And well, in the work of Ittinghoff, Frenkel, Kashtan, it is proven that in the end of the day, quite remarkably and non-trivially so, it doesn't really matter sort of the space, the solutions to these problems basically turn out to coincide, but that is of course something that isn't quite obvious from the start. It is something that arises a posteriori after some non-trivial amount of work, and that is in particular the what is contained in the important work of Ittinghoff, Frenkel, and Kashtan. So, okay, I discussed yesterday sort of my take on this subject based on the single valuedness condition alone. An important thing was that we introduced the operation. We used the relation between, so, okay, very briefly. So the steps were to map it through the so-called separation of variables transform to these differential equations that define operas. And then, well, one is to find single-valued solutions to these differential equations, and this turns out to be provided by the so-called real operas, that is, operas with real monodromy. So one can rely on the mathematical classification of the so-called real projective structures, thanks to the one-to-one correspondence between real operas and real projective structures that we had reviewed. And then there's this important operation called grafting, which basically is starting from a basic opera, which is provided by the uniformization. It allows you to construct a discrete infinite family of real projective operas. And Goldman's theorem then asserts that this is giving all the real projective structures or all the real operas. So in some sense, yeah, it is like the creation of all the excited states from a ground state, and that is indeed sort of in the integral model interpretation then a natural interpretation to have. So now I had promised that to start this lecture with a very brief, necessarily, review of the work of Ittinghoff, Frenkel, and Kashtan. And well, as sort of anticipated already, well, the key point there, and this is what makes it so interesting and deep, is to introduce aspects of harmonic analysis into the geometric Langlands context. So up to now, we have been talking about just the constraint of single valuedness only. But the next step then is to introduce a Hilbert space. And then what we can ask for are solutions to the Hitchin eigenvalue equations, which are square integrable. So briefly, and here really I don't want to go too much into the technicalities. This is just to give you some impression on how this works. Actually, here we are making contact with a lecture of Edward Witten, who has also discussed this from the gauge theory perspective. So what one considers initially is, well, a stack of bundles, a version of bun G where one considers the stack of bundles with automorphisms in the center of the group G. And then one defines from that a coarse moduli space by, well, roughly speaking, forgetting about the automorphisms. So this is a smooth moduli space denoted bun RSG of C. That is sort of the arena on which then the constructions of eating of Frankel take place. And on that moduli space, one can introduce a line bundle of half densities by this sort of funny way of taking absolute values squared with the line bundle, which is here then the K1 half, which is exactly the line bundle on which the quantized Hitchin Hamiltonians act. And this is then defining what is called the line bundle of half densities. Associated is the space of smooth compactly supported sections of this line bundle of half densities. It plays a role somewhat analogous maybe to a Schwartz space in harmonic analysis. And then one can define a Hermitian form on the space S sub G by integrating with respect to a natural measure. Well, that is of course applied here in the definitions, by integrating over bun G RS, this product of V with the conjugate of W bar. And this space SG, by its definition, is then a dense subspace of the completion with respect to this Hermitian form. So thereby, basically, here, in plain English, is the definition of the scalar product by integrals over bun G, and this defines the Hilbert space that we want to work with, or that Ittinghoff, Frankel, and Kashtan work with. And then the work of Ittinghoff, Frankel, and Kashtan is formulating a set of conjectures, which in some important and kind of prototypical examples are actually proven. And the resulting picture is as follows. You can consider eigenspaces of the Hitchin Hamiltonians, which are generated by the single valued solutions to the pair of eigenvalue equations, say the holomorphic Hitchin eigenvalue equation and its antiholomorphic partner. And these eigenspaces, the eigenfunctions are contained in this Hilbert space, so they are square integrable, good news. They are at most one-dimensional for given eigenvalues, so there is sort of no degeneracy in the spectrum. And furthermore, that is something that in sort of my approach was assumed from the outset, but which Ittinghoff, Frankel, and Kashtan do not assume from the outset. This eigenvalue of the conjugate, the complex conjugate Hitchin Hamiltonians is in fact, as you might have expected, but well, if you think about it, it's not so obvious in the end of the day, well, that the eigenvalue for a non-trivial eigenfunction of the complex conjugate Hitchin Hamiltonians is in fact the complex conjugate of the eigenvalue of the Hitchin Hamiltonians themselves. Well, and furthermore, these Hilbert spaces do decompose as a direct orthogonal sum over the eigenspaces of the associated to the eigenvalues chi and chi bar. All right, so that is a statement of completeness. And there is a considerable strengthening or deepening of the story, which one gets by introducing the Hecke operators. That is a subject that in the ordinary context of the geometric Langlands correspondence, unfortunately, I was cutting extremely short, basically almost skipping it. Let me give the flavor very briefly here of the construction. So the Hecke operators are defined on these, well, the sections of this line bundle of half densities by, well, this type of so they're represented as integral operators, where what appears here, what are the key players? So here one wants to act with a Hecke operator on, say, such a half density, thinking of it as, say, a locally defined function on the modular of bundles. So we can think of an evaluation on a particular bundle E. And then associated to such a bundle, well, you can look at the space of all lambda Hecke modifications. So the Hecke modifications are classified by points in some orbit in the Grassmannian, which well, looks as here. So, and this is in turn classified or parametrized by the weights of the Langlands dual Lie algebra to the original Lie algebra G. So what one is integrating over here is basically one is integrating over all possible ways of, say, modifying this given bundle E. And this is the same as integration over such an orbit in the Grassmannian, or its closure. And here, well, one takes the pullback of the function f under the correspondence between the respective bundles, which is defined by the Hecke modifications that are parametrized with by the points in this orbit. Okay, so this just to give you a flavor. Of course, it takes a little more time to unpack this in full, but perhaps it gives you some idea. So it is not integrating here over all of bund G, but over orbits of of Hecke modifications. All right, so this gives us another set of operators acting on these sections of the line bundle of half densities. And among the conjectures or theorems of Ittinghoff, Frenkel, and Kashtan are the following statements. Well, the Hecke operators extend to a family of commuting compact normal operators on that Hilbert space they have introduced. The Hilbert space decomposes into eigenspaces of the Hecke operators, and the eigenspaces of the Hecke operators coincide with the eigenspaces of the Hitchin Hamiltonians. So in this analytic context now, the Hecke eigenvalue, which was a, say, categorical one in the original, the Hecke eigenvalue property, which was a, say, categorical one in the original geometric Langlands, becomes really a sort of more classical one in the sense of harmonic analysis. And again, well, and in the end of the day, one of the main statements they arrive at is that the eigenspaces H chi chi bar of, say, well, both the Hitchin Hamiltonians and the Hecke operators are non-trivial only if we have a real operator and the chi bar is the complex conjugate. So in the end of the day, this is the statement that indeed the type of eigenstates or eigenfunctions of the Hitchin Hamiltonians that are described in this context are actually is the same space, the same eigenfunctions as what was already singled out by single valuedness condition. But that is, of course, a very non-trivial fact that, it suffices, I mean, basically it says it suffices that the condition of single valuedness is already strong enough to ultimately identify the same set of eigenfunctions. All right, so what I just want to mention before I leave this lightning review of the work of Ittinghoff, Frenkel, and Kashtan is that what they use is a lot of results from the previous work on the geometric Langlands correspondence. That is what furnishes the the groundwork for this functional analytic extension of the Langlands correspondence that they call the analytic Langlands correspondence. So I think, yeah, the nice perspective that opens up is that the story continues and will turn into more and more rich interplay between these algebro-geometric aspects that have been pushed extremely far already, and sort of the analytic aspects, which have become a new topic of research in this direction. All right, so here's a kind of schematic view of the emerging picture, which I just want to very briefly say to round off sort of this second part of my lectures, present as a kind of executive summary of what has happened up to now. So the analytic Langlands correspondence becomes a correspondence between real operas and then either single valued or L2 normalizable Hitchin eigenfunctions. And there's a nice sort of dictionary emerging between, say, the perspective of the Langlands correspondence, the Langlands program, and quantum integrable models, sort of from the D modules, which represent in the integrable model context the commuting Hamiltonians one aims to diagonalize, or in the context of automorphic forms, these would be the Laplacians. And then sort of there are non-local operators, which in the context of Langlands are the Hecke operators. In the context of quantum integrable models, one would call them the Baxter-Q operators. That is some analogy that one can make pretty precise, but I don't have the time to do this. And then, well, concerning the eigenstates, there is a distinguished state, which is represented by the uniformizing oper, and that would represent sort of the natural ground state in this problem. And then grafting is the operation which sort of creates from the ground state all the other excited states. So that is the picture we've arrived at. All right, so maybe quickly I should ask for questions before I go over to part 3, which is about a quantum version of the analytic Langlands correspondence in the relation to SUSY Q of T. So I see Aswin has a question. Well, okay, so I will come to this, in fact. It's probably the same, although there are some aspects left to be clarified about this relation between the integrated Hecke operator and to the degenerate fields. So that there is a relation, I think, can be inferred on the one hand from the relation, from the description of the Hecke functors in the geometric Langlands correspondence in the work of Balasubramanian and Greenfeld, and they had an explicit relation to degenerate fields in this context. And well, there is definitely then the link between the Hecke functors in Balasubramanian and Greenfeld and the Hecke operators in the analytic Langlands through the geometry defining these operators via Hecke correspondences. So this is also pretty clear. I think to round off the story, what one should do is really to clarify really the precise relation to degenerate fields. So one should simply be able to shortcut this kind of chain of relations that is implied by what I just mentioned. So, right. And okay, so maybe that's about that. There's another question. What is the relation between the eigenvalue of the Hecke operators with the eigenvalue of the Hitchin Hamiltonians when the eigenspaces coincide? That is also a good question. The eigenvalue of the Hecke operators will basically be given by the solution to the equations defined by the operators. So the eigenvalue to the Hecke operators, when you vary the point at which the Hecke operator is defined, I call it P prime. So when you vary this, it will satisfy exactly this upper differential equation. So this du squared minus T of u acting on this eigenvalue equation. So it is very closely related. This is in some sense what makes it so nice, that this eigenvalue property gets really particularly direct in this context. All right, I do not see further question, but interrupt me if you want to hear more or if you have further questions anytime. So let me start part 3. I have to perhaps speed up a little bit, but anyway, what is it about? It's about the quantum analytic Langlands-correspondence relation to SUSY field theories. What do I mean by quantum geometric Langlands-correspondence? So very briefly, well, there has been a one-parameter deformation of the Langlands, of the geometric Langlands correspondence discussed both from the points of view of mathematics and physics in works of, well, in the lectures of Frenkel, there is a discussion of such a generalization. And then a serious step has been taken by Dennis Gatesbury, that is sort of on the math side, but on the side of physics, there is the suggestion to such a an initial suggestion to such a deformation in the work of Kapustin and Witten, and well, I myself had proposed a perspective on what this can be in 2010. It should be said that it is not as far developed at this point as the geometric Langlands correspondence is, which has been pushed very, very far in some respects in the algebra geometric context. But yeah, the perspective, which I think is, so that is the hope or vision or dream that is shared by all these proposals in this direction, is that this deformation that is called quantum geometric Langlands correspondence offers the attractive perspective that the geometric Langlands correspondence would emerge from it as a limiting case, because one has an additional parameter which one can send to, say, 0 in order to recover the original Langlands correspondence. But say, yeah, if you have non-zero values of the deformation parameter, you would see the Langlands duality realized in a somewhat more transparent way. I mean, that is, of course, rather vague in general, but one place where it becomes a little more visible what is meant by that is when one notes that the feature of this quantum geometric Langlands correspondence is expected to be that on top of the usual Hecke functors that we have been discussing at some points in these lectures, we will from now on call them the magnetic Hecke functors, and they're labeled by the weights of the Langlands dual Lie algebra. There should now be a dual family of electric Hecke functors, which are labeled by the weights of the original Lie algebra. So that is, so here sort of in terms of this duality or these dual roles of these, say, two families of Hecke functors, there is already sort of a incarnation of a very simple type of then this Langlands duality pattern. And yeah, of course, from this point of view and from the point of view of this, well, the emerging picture, it's a natural question whether there is an analytic version of the quantum geometric Langlands correspondence. So now we're trying sort of to push it in this direction as far as we can. And yeah, here comes a proposal for what I believe this should be in the case of SL2. I'm not, again, discussing sort of the case of a general Lie algebra, although at least sort of the basic outlines and so on can be quite easily generalized to more general Lie algebra. So the guy I want to introduce now, which is called the H3 plus Westman-Witten model, has partners or counterparts in which the role of SL2 is replaced by more general Lie algebras. So I start with a physics perspective, but I will offer a perspective that should be more understandable to mathematicians, basically immediately on the next slide. So the physics perspective starts with a path integral, and for these theories here, for the theory we're talking about here, which is called H3 Westman-Witten model, this has been initially studied by Krzysztof Gawęcki And basically the idea was to make a step towards the world of non-compact Western-Witten models by simply replacing in the action of a compact Western-Witten model the group valued field, which takes values in a compact Lie group, by by maps from the Riemann surface to the hyperbolic 3 space. So it makes perfect sense to evaluate the Western-Witten action on such maps. And in fact, it simplifies. So this business of the topological term is absent in the case of this, say, non-compact symmetric space, which is the hyperbolic 3 space. But okay, all this I don't really need to discuss in any detail. Here is a concrete, say, explicit representation of the action functional in terms of a particular choice of coordinates for the hyperbolic 3 space. So with this, the action functional defining the path integral is perfectly precisely defined. And then then there is a class of observables, which is distinguished by particularly simple behavior under the symmetries, which is the loop group associated to SL2C, the non-compact group SL2C, and they look like here. So the field is here, and X are some auxiliary parameters that you introduce as a convenient gadget to parameterize the families of fields of our interest. So that is sort of, in a nutshell, the path integral definition a physicist may like of the H3 plus Western-Witten model. But okay, the usual comments apply. Path integrals are in general hard to define rigorously. So even if this provides a good starting point for many physical investigations of this model, it is not as yet representing a rigorous definition of the model from the point of view of a mathematician.
Sorry.
But anyway, yes, there's a question.
I probably missed it. So does H3 plus the three-dimensional hyperbolic space, does it have a structure? Does it have the structure of a group?
No, it does not have the structure of a group. It's a symmetric space. But anyway, nevertheless, you see, you can just, nevertheless, you can evaluate the Western-Witten action on such maps.
Using this matrix
if you
H.
want to, yeah, just on this matrix H, right? So it's just the evaluation of the same action on these matrix valued functions H. And well, of course, the details of this you can find discussed in the work of Krzysztof Gawęcki. But okay, you can develop, on the other hand, a representation theoretic or conformal field theory approach to the same problem. And that ultimately leads to a well-defined mathematical problem whose solution would represent what we physicists would consider to be the definition of this theory. Namely, the way it works, and again, I have to be rough and quick, is we believe to know what the space of states of this model is. Namely, it's the direct integral of principal series representations of the affine Lie algebra associated to SL2C. So that is a little unusual because, the Lie algebra for SL2C, okay, if you just forget about the hat for a moment, then of course we can use the standard trick or observation which is based on the observation that its complexification is isomorphic to the direct sum of two SL2 Lie algebras. And that sort of has a counterpart on the level of the affine Lie algebras. So there is then a splitting of the complexification of this SL2C Lie algebra into left and right SL2 hat Lie algebras, which have generators J and A as before, or J and A bar as before. But the modes which appear sort of in the currents, which we form as generating functions of the Lie algebra generators, they are complex conjugates of each other. So really there is a clear association between sort of these two copies of SL2 hat to the holomorphic and the anti-holomorphic, say, sectors of this model. However, the representation theory of that makes perfect sense. You can just induce representations. I mean, it makes sense mathematically, and it has a algebraic descriptions. You can introduce representations of SL2C as, well, if you like, as mathematician, you would introduce them as the space of k finite vectors in the dual of the tensor product of two Vermas for the SL2 left and the SL2 right, respectively. But, well, you can also just take the physicist perspective and say you take a principal series representation of the finite dimensional Lie algebra SL2C. So just the usual principal series as was intensely studied from the, say, late 40s in the connection to representation theory of the Lorentz group and so on, and then induce from it by the action of the current algebra generators a, well, current algebra representation in the usual fashion. Anyway, all this can be used to argue that the correlation functions that had a path integral definition here have an, say, algebraic or, well, if you like, D-module description of the following type. So, namely, these guys have to satisfy KZB type equations. However, now we analytically continue the level, but, well, apart from this algebraically or from the form the differential equations take, it's just the same, except that you continue a parameter. And however, of course, they're complex conjugates, which are always a part of the game due to the fact that we have here this anti-holomorphic SL2 affine algebra in the game. So yes, we have solutions of the KZB equations. So we want solutions of the KZB equations, but of course not just the most general or arbitrary solutions. We want them to be single valued. That is something that is, well, what you definitely expect just from the path integral to have. So you now sort of axiomatically take it as a kind of defining condition of the space of solutions to KZB equations that you will be interested in. And furthermore, well, these Hitchin Hamiltonians, I mean, we're talking now about the same Hitchin Hamiltonians defining the KZB equations as before, right? Except that we consider, oh, sorry, here is a misprint. This should not be minus h check. This should be the parameter kappa that was introduced here in front of the action. It should not be h check there. Right, but yes, it's the same then differential operators that appear there, except that we have continued k, or this the parameter k, to minus kappa. And well, these have singularities at these wobblies, at the wobbly loci in Bun-G. Well, these parameters x turn out to have the geometric interpretation in this context as the moduli of bundles on the Riemann surface on which we work. And last not least, to single out a good class of solutions who require sort of also a mild singular behavior near the boundary of the moduli space of complex surfaces. So we're talking here, yeah, about the, I mean, the KZB equations were describing the variation of the complex structure moduli of the Riemann surface of. So to sum up, I mean, basically what from this arises is basically the tentative definition of these correlation functions as single-valued, tempered conformal blocks of the SL2C hat Kac-Moody algebra, which, well, by its nature, basically combines the left and right, or holomorphic and anti-holomorphic affine algebras in it. Okay, so if you wish, well, it reformulates the problem to define the H3 plus Westman-Witten model as basically the problem to solve, well, the quantum analytic Langlands-correspondence in this sense, right? So you can take it to be here again as being a problem to find single-valued solutions of certain differential equations defining sort of the D modules which appear in the Langlands correspondence, with on top of it the single valuedness condition imposed and some conditions on the singular behavior near boundary of the moduli space imposed. So, okay, so this is sort of what I try to substantiate a little bit on the next slide, namely what has it to do with a quantum analytic Langlands correspondence, which is basically by reminding you of, well, on the one hand, that the analytic Langlands, the analytic geometric Langlands correspondence was about finding single valued eigenfunctions of the Hitchin Hamiltonians, and furthermore that the KZB equations can be considered as a natural deformation of the Hitchin eigenvalue equations, in the sense that here are the KZB equations recalled, and when we take the critical level limit, then thanks to an ansatz of this form, we see that sort of in the next to leading order part, where we find the most interesting information, well, we recover then in the critical level limit the Hitchin eigenvalue equations. So it is in this sense that the KZB equations can be seen as a deformation of the Hitchin eigenvalue equations. All right. And so, yeah, in this sense, indeed, correlation functions, yes.
There is one question from Aswin. So which part of 1, 2, 3 corresponds to tempered condition in the previous slide?
Well, tempered now sort of is meant to refer to number 3. Because, yeah, that is how it was meant to be understood here. The tempered is basically, I mean, I'm not 100% precise here. I should specify really what is the smart singular behavior. It has to do with, well, the types of, say, conformal dimensions that would, say, represent, that would correspond to the intermediate states in a factorization near the boundary of DD in Mumford moduli space. And this in turn is determined here by the set of representations which appear in this direct sum, direct integral decomposition of the space of states. So this is what predicts that the behavior should be relatively mild, like for example in Liouville theory. And yeah, this is what I here refer to as a tempered, which is a loose analogy to the use of the word tempered in harmonic analysis. But well, anyway, take it as a definition if you like. Okay. Well, from that perspective, right, the question that immediately arises is, do such guys exist, right? So I have basically reformulated the problem to construct the H3 plus Wessel-Witten model as the problem to find solutions to these conditions. And I guess the first question we should ask, do solutions to these conditions actually exist? Do we know they exist? And well, thanks to some sort of amazing developments, well, I mean, in the combination of two sort of developments, one of which I find truly amazing, the answer is yes. And the point is, well, this is something which we know already for quite a while, so it's not so new and exciting anymore. But the first step sort of towards the solution to the answer of these questions is provided by, well, something that looks like we've seen it before, namely we know that there is an integral transform that relates solutions to the Knizhnik-Zamolodchikov-Bernard equations to the BPZ equations of conformal field theory. So this a priori is really, well, again, you see here, this is just to be seen in analogy. Well, it's more than an analogy. It's just a deformation of this separation of variables transformation that we have been discussing a little bit in the context of the analytic Langlands correspondence. There we had here on this side, we had the Hitchin eigenfunctions. And then there was a kernel without a parameter kappa now we deform it a little bit, but it is then, well, given by basically the same formula, which we can find in the literature. And then in the SOV context, this here was given by this product over solutions to these upper equations, which in the end were related to, well, uniformization and grafting. Now, the whole point here is to observe that all this on the level to begin with of the differential equations, it has a deformation away from the critical level, where the left-hand side is solution to KZB equations, and this is what we want to have for H3 plus Westman-Witten model. So here, sort of tentatively, I take this as basically a way to define the to-be-defined correlation function. But here on this side, there's something that we believe we know relatively well. There's an explicit kernel. Well, sorry, I didn't write it on the slide. It's a little ugly formula, but it exists. And what comes here, just from the solution, just from the relation between differential equations that you can prove, must be solution to the BPZ equations of conformal field theory, BPZ after Belavin, Polyakov, Samlochikov. And, well, they can be written in this form here. There is, well, the second derivative with respect to variables u, and then a differential operator, which depends on, okay, the variable u, which is a certain, I could write it also, I mean, it's very well known, of course, in conformal field theory. It's a certain first order differential operator containing derivatives in the variables u, as well as derivatives in the variables z. And yeah, so this is then supposed to annihilate these objects. So the first point is, yeah, this is then sort of just a, well, correspondence of differential equations. What it allows us to do is to basically, if we are able to come up with solutions to these differential equations which have the right properties, then we can use this transform in order to produce the solutions to KZB that we're after. Furthermore, well, as was stressed before, this transformation can be seen as a deformation of the separation of variables transform. And, well, the way it is written is supposed to stress the deep relationship between these BPZ differential equations and the operas. Namely, really, the operas can be understood as the classical limit, which is the same as the critical level limit in, well, taking into account the relation between parameters of the BPZ differential equations of conformal field theory. So, well, okay, you can check it from the differential equation explicitly if you want in genus 0, and there's a general machinery basically ensuring analogous statements even in higher genus. So that is basically all relatively well known. To be precise and clear, this transformation really is sort of worked out in genus 0 up to now. However, I would believe that yeah, it's a matter of a little bit of additional work, a little bit more of time to work it out, to work out its counterparts in higher genus as well. Anyway, so we have basically translated the problem to construct the H3 plus Westman-Witten correlation functions into the problem to find the solutions to the BPZ equations. Well, we think we know which guys do the job. These are the Liouville correlation functions, and these have been studied a lot. So we could map single valued solutions. There's a question, yes?
Yes, yes. Aswin asked a question. Are these any degenerate field on the Liouville side?
Of course, yes. I mean, on the Liouville side, there are degenerate fields, and of course, well, these are the solutions. I mean, this is sort of the representation theoretic origin of these differential equations. Good, so this is just lightning sort of definition of the Liouville correlation functions that are relevant here. I see some misprints. These should be u here in the variables, but anyway, there's again a path integral defining that we believe can define the Liouville correlation functions which are relevant in this context. And well, somehow due to, and this is what I find kind of striking, I mean, I myself have been working on the definition of Liouville theory for a while, but by now, really, due to some rather different methods, this has become a piece of mathematics. So this path integral by now is a path integral that mathematicians know how to define. And that was first done in the work of David, Kupian, Rodes, and Vargas. And then they used this definition to basically push the bootstrap all the way through. So to construct energy momentum tensor, etc., and to prove that the well-defined, rigorously defined path integral actually satisfies, for example, BPZ null vector decoupling equations, that it satisfies the bootstrap constraints, etc., etc. So that is the outcome of a series of papers, some of which were published in journals like Annals of Mathematics. So it is by now really essentially, I mean, the last one isn't published yet, but it is basically accepted as a piece of mathematics, the path integral of Liouville theory, thanks to the work of these people. So, and there, well, I mean, somehow the point I simply want to make is that we can just now feed this as a well-defined object here into this construction, and thereby use this formula in order to construct the relevant solutions of KZB equations that we're after. So yes, the solutions to the KZB equations, which we called single-value tempered conformal blocks, which according to this philosophy I'm proposing here represent the objects of interest in the quantum analytic Langlands-correspondence, they do exist mathematically. So this I wanted to stress. Anyway, well, I don't have very much time left. I want to talk briefly about the remaining ingredients, and here I'm basically addressing one of Aswin's previous questions. So in this context, yes, we can also talk about Hecke operators. So here I'm briefly returning to the discussion of geometric Langlands following Bailey and Drienfeld from the first and second lecture. I had mentioned in passing that Bailey and Drienfeld had identified the Hecke functors with insertions into the conformal blocks of special representations. They have a construction in terms of, well, the space of sections on some sheaves on the Grassmannian, but we don't really want to talk about this now. I mean, in some sense, this explains somehow how the lambda, that is the weight of G. Langlands dual, enters into the definition of this representation. The first point here is that this description continues away from the critical level rather easily. And that is, of course, some observation that already Bailey and Drienfeld made in their work. Furthermore, they have identified the representations here, and that is a non-trivial theorem of theirs, with irreducible High's weight modules of the affine Lie algebra with this weight here. So there's the lambda, and then multiplied by this factor k plus h check, which is appearing all over the place here. These are degenerate representations of affine Lie algebras. And so in particular, for example, so they have null vectors, and in some simple cases, you can compute them explicitly. So for example, when you take lambda equals 1/2 as the weight of G. Langlands dual and consider SL2 as your Lie algebra, then it is just created by J minus 1 minus on the highest weight vector. And there are fields that we know associated to it in the H3 plus Westman-Witten model. Thanks to these null vectors, they satisfy additional differential equations, which presumably is crucial for making explicit and more, say, transparent their relation to the Hecke modifications. But anyway, for the moment, we just use they satisfy additional differential equations, and the terminology, the jargon is that such fields are called degenerate. You can see what happens to them under this quantum SOV transformation. That was the transformation between Westmüller-Witten and Beerwald theory, H3 Westmüller-Witten and Beerwald theory. Well, no wonder they are mapped to degenerate fields of the Virasoro algebra. In this case, the degenerate fields that, according to some standard notations, are called the ones of type 1, n, which satisfy PPZ equations. We will call them magnetic in the following. And then there are some fun games that one can play with the degenerate fields, which have a nice history, a long history in conformal field theory. They go back to the ideas of Eric Verlinde, leading to the famous Verlinde formula. And they have attracted, in the context of AGT correspondence and generalizations, some renewed attention. And I think there it was really understood how important these guys are. So the idea is that thanks to sort of the differential equations that these degenerate fields satisfy, you can prove, I mean, you can see how they behave when they get close. There's the notion of fusion. They can annihilate into a vacuum representation. So you can sort of study a process in which you pair create such degenerate fields from the vacuum representation by some operation which I would like to call bubbling. Then you can say move one of these pair along a simple closed curve on the Riemann surface, and then you can re-annihilate them. And depending on what you consider conformal blocks or full correlation functions, it will leave an effect on either conformal blocks or correlation functions. You will not end up with the same one as before. And the beauty and importance in this context comes from a fact which then can be shown on the basis of these constructions and explicit computations, that the Verlinde line operators generate an algebra, so you can compose them, multiply them, and so on, representing a quantization of the algebra of functions on the character variety of flat PSL2 connections. All right, and here again now in our business, we have some options, some choices. We can, for example, play on the Liouville side with the degenerate fields of type 1, n that we called magnetic. So these were the pre-images of the Hecke fields under the SOV transformation, and that is a natural way to define what you could call magnetic Verlinde line operators. These are the guys which then become classical, that is commutative in the critical level limit. So in some sense, well, it gives a bridge between de Rham and Betti versions of geometric Langlands, because yeah, it relates somehow this local system in the sense of pair bundle connection to the topologically defined character variety. Anyway, there are these guys that we can play with that play some useful role. But really the main point I want to get to is that there are the other guys, namely there's another family of degenerate representations, which are in some sense from the point of view of H3 plus Western-Witten model even more basic, namely those where we just have here spins, which are half integers labeling the representations and thereby the fields of the H3 plus Western-Witten model. So there's no factor k plus h check here. Well, this is why then they are called electric. And furthermore, it can be shown with a little bit of thought that the SOV transformation will map them to the other type of Virasoro degenerate fields, namely of the type m,1. So it makes, I guess, perfect sense if we call the other guys magnetic, then this is sort of a dual series of degenerate fields. Let's call them electric. And we can play the Verlinde game. We can play the Verlinde game of bubbling, continuing along simple closed curves, re-annihilating in order to define a family of natural and useful operators acting on conformal blocks as well as correlation functions. Furthermore, let us observe that, well, by the description, these Walinde loop operators are associated to simple closed curves. But you can, of course, easily generalize these to, say, integer measured laminations, because these were just, well, collections of curves which don't intersect. So, of course, you can do the game of bubbling, continuing, and reannihilating whenever you have a collection of curves that don't intersect each other. Then you just do it, well, basically repeatedly or recursively, and you thereby define Walinde line operators associated to laminations. We've seen laminations before. They played an important role sort of in the classification of the real operas. And now we can do it sort of on the level of conformal field theory. So a claim I want to put forward, and that is work in progress, basically based on these computations of Walinde line operators of Aldiger, Giotto, Gukov, Tachikawa, Walinde, and Drucker, Gomez, Okuda, and myself. And then, of course, yeah, one has to somehow generalize this a little bit and, well, think a little harder. So this is work in progress. But the claim which is emerging is that the insertion of the electric Walinde line operators associated to lamination, when we take the limit that the critical level limit, we recover the eigenfunctions of the Hitchin Hamiltonians associated to that lamination. Right? So we had a geometric construction of basically the eigenfunctions of the Hitchin Hamiltonians at the critical level, and that was part of sort of the analytic Langlands. And what I'm now describing is sort of the natural quantum deformation thereof. And I'm proposing that this is basically provided by the idea of Walinde line operators. All right. So that is a claim. As I said, it's a little bit work in progress. Hopefully something can appear not too far in the future. Okay, so I don't know if the chairman would give me about like 5 minutes. I can very briefly
go ahead.
Through the gauge theory interpretation to round off somehow the discussion.
Yeah, please go ahead.
Okay, thanks. Yeah, it won't take very long. I just want to give you the very rough picture. So what is, of course, known for quite a while now is that many of the ingredients which were discussed on the level of CFT in the last couple of minutes, last half an hour or so, have a interpretation in the context of what is called supersymmetric gauge theories of class S. So we're talking about n equals to 2 supersymmetric gauge theories in 4 dimensions. And such gauge theories are labeled by the choice of a Lie algebra of, say, ADE type and a possibly punctured Riemann surface C. So we're having the same setup or part of the setup that we're dealing with all of the time here. We shall restrict attention to the simplest case, which was most studied, where G is SL2. And then what we have is basically our gauge theory, supersymmetric gauge theories labeled by Riemann surfaces, possibly punctured. And of particular interest in this gauge theory context are partition functions on squashed force spheres. So here is the definition. So it's a 4 ellipsoid, if you like, defined by some equation. And the prediction emerging, I mean, from the important work of Pestun on the localization of these gauge theories, and then Aldiger, Giotto, Tachikawa, was a relation between the partition functions on these 4 ellipsoids and correlation functions of the Liouville conformal field theory, assuming some dictionary between the parameters, which I don't specify here explicitly. All right, and then in subsequent work, what has been studied are various types of defects. And of particular interest are surface defects. And in this context, we can consider surface defects supported on, say, 2 ellipsoids that we can embed into this 4 ellipsoid. So, well, we can, for example, consider this constraint, and this defines us one of the 2 ellipsoids, which still keeps a parameter, say, epsilon1. We have these 2 parameters, epsilon1 and epsilon2, giving sort of inverse radii of circles that you can draw on this 4 ellipsoid and so on. And yeah, so we have these two choices. We can either set this variable to 0, that's the W variable, say we use to describe the 4 ellipsoid, or the other one to 0, defining 2 ellipsoids on which we can wrap then surface defects. And there are sort of two types of surface defects which have been discussed. One is associated sort of to points on the Riemann surface. So these are here contained, I mean, the choice of the points are contained in some tuples of or divisors of points on the Riemann surface C. Here, that is the capital U and the capital V. And these label the defects according to the work of Alde, Gayotto, Gukov, Tachikawa, Valinde. And yes, what they proposed is that this is then given by correlation function in Liouville theory involving degenerate fields. And various, I mean, a lot of work, I mean, it's impossible to write all the references here, has been devoted to checking this by more detailed localization computations and so on and so forth. The interest of main, I mean, the defect of main interest for us is associated, well, we call it the defect type 2, or codimension 2 is an often used terminology, which is another type of defect which you think of as being wrapped on the Riemann surface. So it is delocalized on the Riemann surface, but it has parameters x in gauge theory related to singular behavior of the gauge fields of the class S gauge theory near the support of the defect. That is a physical way to introduce the parameters. But yeah, following work of Alde, Tachikawa, and then many others, Kuchar, Praschetti, Willard, our chairman, and there's important recent work which basically proves many of the previous conjectures, in particular proves validity of KZB type equations for the gauge theory partition functions due to Nekrasov and Nekrasov-Tsymbalyuk. Anyway, that gives sort of, I mean, this is on the level of conformal blocks / instanton partition functions, but there's also evidence for the conjecture, at least, that if we consider then the partition function on the 4 ellipsoid, that this would correspond to the non-holomorphic physical correlation function of the H3 plus Witten model in this place. This is not yet 100% proven, but I take sort of the gathered evidence here as evidence in favor of this conjecture. Well, and furthermore, there's line defects that we can sort of that we can wrap on these, say, embedded 2 ellipsoids along the two possible equators. And well, what in all this work also has been discussed are support for the conjecture or proofs in some cases that these line defects correspond to the Valinde line operators in the Liouville theory. And basically now, simply to finish the lecture, I want to go sort of the last step in this story. Namely, I want to observe that it does seem to make sense to consider simultaneously a surface defect of type 2, which was sort of getting this uplift to Witten, and line defects. So that is sort of on this 2 ellipsoid, and then there is one a line defect on the equator of the other 2 ellipsoid, because then the supports of the surface defect and the line defect would not intersect. So you wouldn't therefore expect problems with defining such things on the gauge theory side. And furthermore, if you just look at this resulting picture, there's a kind of immediate conjecture that suggests itself. If you have this combined system of defects, namely line and surface defects, there is something natural that we can associate to it on the side of CFT, which now is the H3 plus Witten model. Namely, well, without the line defect, we had here conjectured it corresponds to correlation functions of H3 plus Witten model on the basis of, well, KZB equation satisfied, single valuedness, and so on, these type of arguments. Now the question is, if we on top of it have these line defects which are labeled by laminations, what can we put here? Well, there is something we can put here, namely the thing that we get by acting on the Western-Witten correlation functions by the action of electric Berliner line operators. That is something that makes sense in CFT, and it seems to be the basically only natural candidate I can think of for what can appear in sort of the ultimate version of this correspondence on the side of CFT. Okay, so let me finish with this slide. That is sort of the concluding slide. So there is an emerging picture, and a perspective from which it may be particularly attractive is the perspective of the Nekrasov-Shatashvili program, which relates SUSY QFTs to integrable models. So it basically views the these results, for example, that were initiated by AGT and followers, as a kind of two-step deformation of the integrable structure that one has in Joerg-Witten theory. And now it seems we're reaching the point where we can push it to a natural completion. So here's the dictionary. Maybe for reasons of time, I don't walk through it completely again, but we see here then now a third column, which is related to SUSY quantum field theory with a surface defect, the local observables corresponding to the Hamiltonians. The Heck operators would be one type of surface defect of the type 1. But now the most interesting news I think we can propose here is that we can basically relate this operation of grafting, which was creating sort of the higher eigenstates of the Hitchin Hamiltonians to the insertion of certain line defects on the gauge theory side. Let me skip this. There is something interesting of potential and Yang functions and so on that one can also then get basically almost for free when one was thinking about the CFT and sort of classical limits or critical level limits of this setup. And yeah, so the main sort of philosophical remark I want to end with is that, yeah, it is basically this extended setup involving various types of defects, which makes really all the aspects of the integral structures of n equals to 2, d equals 4 supersymmetric quantum field theories fully visible. So it is the interplay of the various defect observables which sort of pushes it to a natural end by, in particular, providing also sort of the creation operators generating the full spectrum from say a ground state. Okay, with this I'm done, and thank you for your patience, and thanks for listening.
Thank you very much. Questions? If you have a question, just type in the chat, or if you can, unmute yourself. So I have a quick question. How do you define the Fellinde loop operator in West-Zumino-Witten model? Do you have some degenerate field in the West-Zumino-Witten model?
Yeah, so this is basically, this is indeed basically the same idea, but it just replaces the degenerate fields of Virasoro by it just replaces the fields of Virasoro by the degenerate fields of Kac-Moody, right? So in particular, it's particularly simple because the basic one is this what is corresponding to the spin 1/2 representation, and I mean, it's the same. It's the same type of calculation, right? Because what you can do is simply to observe that if you insert this into the conformal blocks, then you have this additional decoupling equation. In that case, it's just a second order, very simple differential equation, which allows you to reduce computations to say hypergeometric functions and so on. It is closely analogous. And it uses the same idea, basically. Is it clear enough, or shall I elaborate more?
Yeah, it's clear. It's clear. Thanks.
Okay. There's a question I see in the chat now. There is it's about sort of the reference we cited, which is a paper of Stoyanovsky on this relation between KZ and KZ and BPZ. This is indeed apparently having a funny history. First, if you just want to really look up this original reference of Stoyanovsky, what you can do is the archive keeps previous versions. So before it was withdrawn, I mean, you can find the versions which are there before it was withdrawn, and you can read them, right? You can download them and say, as far as sort of this relation between differential equations is concerned, there's nothing wrong with this. I mean, I was told from Edward Frenkel that sort of, well, this arose out of the discussions that the three, that is Fagin, Frenkel, and Stoyanovsky had at the time. And then Stoyanovsky was writing up part of that. And I think this unclearness of some notions on which the material is based is really referring to, well, the fuller vision of a program, say, in the spirit of quantum geometric Langlands-correspondence that was probably in the air. It was emerging already back then. But yeah, it indeed, if you want to make it precise, really mathematically, it requires quite a bit more of work. What we're extracting here from it is just a relatively simple-minded, modest aspect of that, which is this relation between KZ and PPZ. And yeah, if you want sort of the original version, you can find it on the archive. But in the end of the day, it turns out, and this is what is described in later references, including our paper with Sylvain Ribaud, really the key idea is the one of Sklianin, and then just the observation that if you have this deformation provided by KZ equation, well, you need to work a little more in order to ultimately, I mean, there's some factor that you need to factor off from the Liouville conformal block in order to find BPZ on the nose. And good, so there's a little more work, but that is not sort of, I mean, there's no problem about that. And so I hope, yeah, has become a little more clear. Ashwin has a question.
Ashwin has a question.
Yeah, hi. First, thank you for the great series of lectures. So I sort of have like one technical question and one more sort of philosophical question. So would you say the philosophical question first? So would you say the analytical version of geometric Langlands is somehow the first thing that, say, 2D conformal field theorists would even think about? Because in CFT, it's sort of unnatural to look at just the chiral halves, right? It's natural to look at the full CFT correlator. So is it just some historical thing that people looked at the categorical version first and the sort of analytical version later? That's a philosophical question. And the technical question is, you gave a sort of proposal for the temperedness condition. Do you also have a proposal for what it means to be cuspidal? I would assume this is the kind of setting to ask both of those questions, right? What do those adjectives mean?
Yeah. Okay, good. Yeah, let me pick an order, which is maybe chronological. So the first was philosophical, right? So it's amusing, and I'm not sure whether I can do justice with my answer to, to the history here. My understanding is, well, in the categorical version, I mean, what's the point about sort of talking about D modules rather than analytic functions? And this is what sometimes the colleagues from the algebra geometric community, well, they do stress or admit. I mean, the point somehow is that it may be very hard to actually describe concretely what the solutions are to the differential equations, their monodromies, and so on. That is even with relatively simple differential equations, it can be a much harder task than sort of describing the differential equations themselves, relations between different systems of differential equations, etc., etc. So in some sense, I think I'm not sort of doing these colleagues which too much of injustice by saying that in some sense the problem of studying analytic aspects was postponed by, in a first round, focusing on the D-module aspects, which, I mean, after all, are foundational and in some sense to treat the subject in some generality, you will it will be the basis sooner or later, and so on and so forth. So, and yes, I think it is simply, it started when realizing that in a context like this critical level conformal field theory and so on, it may be out of reach to really construct explicitly the solutions to the Hitchin eigenvalue equations, but you can say a lot about the differential equations and how they behave, and make deep statements like Hecke eigenvalue property and so on. So this is why sort of in this stage, I guess a shift happened to this categorical version, which just seemed to be the right framework for, well, for this setup and for subsequent generalizations. And well, perhaps then it's a little bit like it sometimes happen with mathematics and physics and so on. Then, I mean, this was pushed very far, and perhaps people had temporarily forgotten for a while that there may be interesting analytic aspects ultimately, and that they may bring the subject back sort of to the origins and sort of to the analogy with the theory of automorphic forms and so on. But I'm sure that people like Kashtan and so on had never forgotten this, and were then perhaps kind of happy to have I mean, when there was a chance to return to this and produce an analytic theory, which, well, in some sense adds yet another kind of layer to the story, or yet another level to the whole story. Okay, so this was sort of the philosophical thing. I'm not sure if I have completely answered this, but perhaps partly at least this is my very personal view or understanding of this. I mean, again, let me stress that I expect all these, or most, or a lot of these like categorical and algebra geometric things to become relevant for the analytic story as well, or sooner or later. So I think it will be sort of really in the sense of adding another layer of, say, or a deeper layer, or whatever, however you want to see it. Good, then, sorry, second question concerned temperedness, cuspidal, and so on. I mean, here again, yeah, I think what we have to face is the situation. There are these notions like temperedness and cuspidal, which have a relatively well-established and traditional meaning in, say, automorphic forms, etc., due to growth of eigenfunctions and things like that. Now, what we've heard, and that is, I think, very intriguing, is that, I mean, in this conference, Dario, for example, had heard that there are analogs of this in the categorical framework. I took myself the freedom to propose a personal sort of version in the context I was talking about of, say, what cuspered and, I mean, tempered, what tempered might mean, and you were asking whether there's also something like cuspidal. Let me first say this, of course, requires further discussion, right? So that is no question that this should be further discussed, analyzed. So it was I can tell a reason why I thought it makes sense in the context I was talking about to use these words, but of course that is not something you should take for granted, and maybe some evolution has to start in order to converge or as a common use of this terminology, and to clarify really to what extent it is analogous to the traditional uses of this terminology in automorphic form. So it is a pretty wide open issue at this point, I should say. But yeah, what I can tell a little bit is, well, I mean, in our what I took as a starting point is that temperedness has to do in the theory of automorphic form with growth properties of wave functions or eigenfunctions near singularities. It is a little more tricky here because we have here now two types of dependencies in the game, one with respect to the complex structure moduli, one on Bun-G. And the types of singularities that occur there are quite different. The temper that I used refers to the singular behavior at boundary of the Lean-Mumford moduli space for Riemann surfaces. In some sense, if we think about these analogies, it doesn't really have a very direct counterpart in the theory of automorphic forms, because we don't really have, I mean, we have here, I mean, what is pretty much analogous is basically the space for which I had used variables x, the Bun-G. That, of course, for example, would correspond to the upper half plane, say, in the simplest case of theory of automorphic forms, right? Because Hitchin Hamiltonians would then be replacing Laplacians and so on. That is roughly the analogy. So Bun-G is like upper half plane. But now we have basically, we're fibering the upper half planes over Bun-G, over the moduli of Riemann surfaces, and are also studying the behavior with respect to this dependence. This was what my word tempered referred to. You may like it or not, but okay, now I clarified. About cuspidal, well, I didn't use the word, but of course there is a kind of, it is tempting to propose that this should have to do with the singularities on Bun-G. And that, of course, should have to do with the behavior of eigenfunctions near wobblies. Okay, so maybe here it stops. Really, it is something that should be left for clarification in the future. I hope to have clarified a little bit by my words.
Right. So I believe in the geometric Langlands setting, on the local system side, cuspidal does have a simple meaning, and that corresponds to the local system being irreducible. So I would hope that has a CFT meaning. I mean, it should. The local system being irreducible is a sort of more tractable condition, I think, and I think that should have a CFT meaning.
That could be so. What I don't understand about this was a question I was asking in Darrow's lecture, is what this has to do sort of with the original sense of cuspidal.
Yeah, so that I don't know. Yeah, so that
is less clear to me, but okay, you can take it as a terminology which exists and related to reducible. That's fine. In the Riem that I understand a little bit, the CFT Riem, I mean, I up to now mostly see, or almost exclusively see, irreducible local systems, to be precise. I've seen statements, I don't have a full understanding of this, but in these reviews of Gatesbury and collaborators and so on, they're sort of saying that in some sense the construction of this full geometric Langlands-correspondence a la Arinkin-Gatesbury, it splits into two parts, which are roughly speaking associated sort of to a part where Balians and Greenfeld does the job, that is sort of the irreducible part, and then another part where something like geometric Eisenstein series do the job. I've seen a statement that there is a CFT interpretation of these geometric Eisenstein series constructions, but I must admit I don't really understand it. I cannot translate it into my own language yet. I've heard this statement somehow, but I don't feel I can really explain it. Maybe it is something. Yeah. Okay. No. Maybe I shouldn't start speculating. So that is what I can say.
Thank you.
Any other questions? Okay, if not, let's thank the yoga again.
Okay, thank you.
Thanks for all the 3 lectures. Nice lectures.
Okay, thanks. So, yeah, I don't know. Maybe I stay a minute if there are